welcome everyone for the afternoon session. I hope you all enjoyed the lunch break. And our first speaker of this afternoon session will be Antoine Georges from Collège de France and from Flatiron Institute. I learned half. We are looking forward to your talk.
Okay, thank you very much, Andrea. Well, thank you for organizing this great workshop. It's a great community. I'm really happy to be back here after a period of time where we didn't get together so often. So what I would like to do today is to try to give you an overview of what I think is really very remarkable progress that has been achieved in the last, let's say, 5 years on understanding the two-dimensional Hubbard model especially from a computational point of view. And the title is a little bit ambitious. So first of all, today refers to November 14. Maybe tomorrow we'll know a little more. So that's the first disclaimer. Really, in a more modest way, this is paraphrasing Jean-Luc Godard, who unfortunately passed away recently. Maybe the talk should be called 2 or 3 things we know about the Hubbard model. Anyhow, so first and foremost, I would like to thank many people who all contributed in a decisive way to my understanding of the field and with whom I've collaborated. So many of them are on this slide. I probably forgot some, and some are in the audience here, for example. Thank you all. So the main message is what I already said, namely, I think there's been a lot of progress, and this progress has taken place over the last few years because of computational studies that brought together different methods to understand the problem, and especially even more than just bringing different methods, having a real handshake between zero temperature and finite temperature method, and I will elaborate a little bit more on that later. But first, let me give you sort of a guiding thread for the whole talk. What I will try to do is to summarize the various things we've learned into a unified picture. And you will notice that there are no units on this axis, because this is purely qualitative. But this qualitative attempt is actually grounded on data. You may think it looks suspiciously similar to the phase diagram of ITC cuprates, but I promise that this is grounded in data. Okay, so what you have here, let me guide you through this thing. This is a sort of concluding plot that is taken out of this recent preprint that we've put on archive, and which is very much the work of Fedor Simkovich, Ricardo Rossi, and Michel Ferrero. And what you see here is temperature and doping, obviously. And we know, and I'm going to review this briefly, and we'll hear more about it, that there is a fierce competition between stripe ordering and D-wave superconductivity in the ground state. So I'll review some of that. There are some question marks here as to how the stripe order evolves as we increase temperature, and similarly on that side, and overall a question mark about this competition. Moving to the finite temperature regime, there is an important region here, which is labeled PG for pseudogap, which depicts roughly a boundary below which a pseudogap opens, and I will come back later to what I really mean by that. There are many other lines here that I won't have time to describe in this talk. I will focus mainly on the pseudogap, on the stripe, and on the D-wave. An important other line here is a crossover where the magnetic correlations switch from commensurate to incommensurate. I'll come back to that later. So we will use this sort of general cartoon to get guidance in the rest of it. So this is the outline. I don't know if I'm going to manage to cover all of it, but I would like first to give you a little bit of a feeling for how this handshake between different methods took place. So that will be perhaps just a glimpse into the methods themselves. Then I will say a few things about ground state issues, mostly T prime equals 0, no next nearest neighbor hopping, and I'm sure that we'll hear more from Philippe Corbos just after this talk, and Uli Schölvöck and several others in the remaining part of this workshop. Then I will move on exploring spin correlations and how they evolve as function of temperature and doping. And in my view, this is tightly related to the pseudogap. I will talk about the weak coupling pseudogap and then the strong coupling pseudogap, and try to report on recent progress, understanding what is the fate of the pseudogap state as we move to low T and making our way to T equals 0. So first, a little glimpse into what has happened on the front of methods. I think at a very broad level, one can categorize the methods into two big categories. So there is a class of methods that starts from T equals 0 and aims at basically compressing the ground state wave functions by various intelligent means, for example, matrix product states, and applying to these variational wave functions a powerful algorithm such as the DMRG. For many years, this method, which is of course remarkable and very, very productive and very efficient, was confined to 0 temperature. But one of the things that has happened in the recent years is that actually there's been extensions of these wave function based methods combined with sampling ideas to move to finite temperature. So if you want, this is sort of the bottom up way of approaching the problem. There is another class of methods which actually look at this problem in a completely different way. Already a question, yes.
For the next, can you explain what does it mean to wave functions at finite temperature?
Well, this will come later in the talk. Of course, it's an ensemble of wave functions which is sampled by sampling methods. So it's really using compression methods to represent the wave function efficiently and sampling through typical wave functions to sample the Boltzmann measure. That's basically the idea. So it's taking the best of both worlds. Okay, compression with MPS and sampling with basically Monte Carlo procedures. So that's the idea. Okay, thanks, Eugene. There's another class of methods that instead of using entanglement as the guiding principle, use a different guiding principle, which is the notion of locality. If you go to high temperatures, things are quite local, correlation lengths are small, and you can proceed from there by making increasingly refined approximations as you go down in low temperature and your correlation lengths grow. And this is the root of all methods based on dynamical mean field theory and its extensions, broadly defined quantum embedding methods. These methods have been pushed down to lower temperature by doing larger clusters, including additional diagrammatics and so on. And the interesting development is that doing this and doing that now allows to have a dialogue in the intermediate temperature regime, which is really a place of great interest, where we can start asking the same questions and hopefully, and as I will see, in reality, getting at common answers. There is a third class of methods which look a little bit transversally into the problem, which is trying to start from weak coupling and move into the intermediate and strong coupling regime. And one of the important progress in this field over the last decade has been the development of various flavors of diagrammatic Monte Carlo, which is again a sampling idea, but a sampling idea which is not based on sampling particle configurations, but sampling the Feynman series, the expansion in terms of Feynman diagrams. Actually, this is already superseded. These methods are no longer sampling Feynman diagrams, they're actually sampling determinants, which has been a definitive improvement in the field. And in simple cases, not yet for lattices, but it's probably coming, they also got rid of the Monte Carlo itself by, instead of sampling, actually using, again, compression method, the so-called tensor train methods, to actually integrate over the internal variables. So diagrammatic Monte Carlo is slowly evolving into a regime where there is no diagrams and no Monte Carlo. And this is actually a very interesting evolution of the field.
So in principle,
Yes.
does it include effects that are non-perturbative in U?
Well, that's all encoded in the radius of convergence of the series. At finite temperature, the series has a finite radius of convergence, and when you are killed by strongly non-perturbative effects, you're not going to be able to converge. So this is not the absolute weapon, you know, but this is very useful to at least move into the intermediate direction. Okay, so the new developments are actually trying to look at this very hard problem of the 2D Hubbard model by combining all these methods together when possible, but also, as I've already illustrated on a couple of examples, importing concepts and ideas from one method into another one, like sampling and MPS compression. And that's much more, even more interesting than just looking at the problem with different methods. Okay, so now to some results. I'm first going to report on work which is not mine, namely ground state issues, zero temperature, and I will mostly talk about T prime equals 0, hoping that Philippe and Uli will tell us something new about T prime different from 0. So this is a phase diagram that was established for the 2D Hubbard model quite recently by the so-called auxiliary field quantum Monte Carlo methods at 0 temperature, which is also a wave function based method, as a function of U and OP, Hall density. And what you see here is a boundary that separates two regimes. A regime where the ground state has spin charge stripes with an ordered structure, and these are the famous stripes that look like this. So we have a spin modulation, which is the red thing, and we have a density modulation, a Hall probability of the probability of a Hall being localized on the site, which is doing this. And you see from this picture that the wavelength of the spin modulation is about twice the wavelength of the spin modulation, and the Hall likes to sit at the nodes of the SDW. So,
the wavelength of the spin should be half.
Sorry?
The wavelength of the spin should be.
No, the charge does this, right? And the Hall is maximum at the nodes of the SDW.
Sorry to interrupt.
Okay. So here on the left we have the spin charge stripes. On the right we have no spin charge stripe. And there is a boundary in between that was determined by this method. Incidentally, this is also something you find in Hartree-Fock, except that in Hartree-Fock the boundary is here. Okay. So stripes are not new. Yes?
So what is the order in the wide region if it's not?
Well, okay, very good question. So these methods just tell you it's a metal, you know, it's just no ordering was encoded in the wave function. We can finesse whether this metal will be eventually unstable to very, very, very low TC superconductor, and probably it should be from coordinate arguments, but I don't want to go into this here. Okay, so that's how you should take it. It's basically deciding when there is stripes, when there is no stripes. Okay, very good. Stripes are not new in the field, of course. They already exist from mean field theory. There are several famous papers from the early days of ITC. These are two of them, one very remarkable one by the late Heinz Schulz. And basically, all the methods that are able to say something about T equals 0 have consistently seen the presence of stripes in the ground state, including single-side DMFT done in an unrestricted way on the lattice, actually. So there is pretty consistent agreement about this. Now, the dicey question is how do these stripe states compete with superconductivity and pairing, okay? And that's a topic on which there's been great progress recently, in particular thanks to the work of some people who are in the audience, like Philippe and Uli. And it's been concluded that there is no superconductivity in the ground state when T prime is 0. And that is because there is actually a very, very delicate competition between the two sorts of wave functions, the D-wave superconductors and the stripe-ordered wave functions. And here you see, taken from this beautiful paper here, a comparison between the energy difference to the vertical charge stripe states of various other states, the D-wave superconducting state, calculated by different methods. And you see that the charge spin stripe ordered state, which is the 0 of energy here, wins by amounts which are basically 10 to the minus 2 times the Hawking. So very, very delicate competition, but with T prime equals 0, it looks like actually the stripe ordering always wins. I would like to say that near this boundary, perhaps not all data points have been collected yet, and I'm not totally convinced if you read the paper that you couldn't rescue D-wave superconductivity very close to this boundary, but this is feasible. This is a matter of actually just doing it. Okay, so this is the situation. However, there is a key player, at least when it comes to comparing two high TC superconductors, which is T prime. And we've known for many, many different studies from the early days of cluster DMFT, but also from, for example, this recent work, which uses DMRG methods that on cylinders, that actually T prime is a very, very important perturbation. You see that the phase diagram on the cylinders varies very much as a function of T prime. So it's kind of an open question. Is the ground state of the 2D Hubbard model a D-wave superconductor at intermediate strong coupling for a range of non-zero T prime? And this is work in progress. I know Shiwei Zhang is working on this, but I'm sure others in the room are actually working on this too. Perhaps we'll hear more about it during the workshop. My guess or bet is that the answer is yes, but I'll see if I'm proven wrong, like in the next talk, for example. Let's see. Okay.
So for conductivity, you mean high temperature?
Yes, that's what I mean.
Always exponentially small.
Yes, that is precisely what I mean.
Can you explain what is SCM, WCM?
What is what?
Notations, like you have this.
Oh, here?
Green one is SCM.
Eugene, I'd rather not explain it. Because I would like to focus the talk on this guy, and this guy. And these are various types of correlated metals. Well, in a nutshell, these are various types of metals. This one is weakly correlated. This one is more strongly correlated. At intermediate regime, at intermediate coupling and temperature, there is actually a change of curvature in the Fermi surface, which is induced by interactions. All methods see that. Nandini has actually studied that recently too. And this is this grain region. But I would prefer not to go into this because in the interest of time. But I'm very happy to discuss it in separate discussions. Okay. So now I would like to ask an additional question, which is, this is T equals 0. What happens when we raise temperature from T equals 0? What happened to the stripes? How do they melt? How does this order melt? Of course, for spin, we have Mermin-Wagner. We know that there can't be long-range spin order at non-zero temperature. The charge for a commensurate filling is breaking a discrete symmetry. So in principle, we expect a finite temperature transition. To my knowledge, this was really not investigated in any form of detail. And recently with Bo Shao, a postdoc at CCQ, and Yun Yaoe and Shiwei Zhang, we actually studied this question, they studied this question using AFQMC. And the answer indeed is that there is a finite temperature transition. So this is this pattern of spin charge order for various values of inverse temperature beta in units of the hopping, inverse hopping. And what you see here when we massage and do data analysis on these plots is that the charge modulation sets in at a temperature scale, which here in units of the hopping for those parameters is on the scale of 0.1 times the hopping. So we need to cool a little bit more, and this is something that is going to happen. Okay? So that's the message. According to this work, and more work is needed on this, there is indeed a finite temperature transition where the stripes melt. Okay. And this is, by the way, also something. Yes, Karen?
What's going on with the spin order in the stripes?
I'm coming to this.
Okay.
I'm coming to this. So this is, by the way, also something which is seen by these methods that combine sampling and MPS representation, the so-called minimally entangled typical thermal state method. And this is another piece of work we did with Alexander Vitek, which actually shows, but of course this is on cylinders, so there is not really a phase transition, but where we see the melting of the charge order while the spin order survives, well, the spin correlations survive, up to much higher temperature. And you see this here. This is from this MET study, the magnetic structure factor. You see that the spin takes over much more quickly than the charge. The charge does nothing down to temperature of the order of 0.1. By the way, this is also the scale at which we saw the phase transition in the AFQMC method. And here the spin coalitions develop at a much higher temperature. In all this range, they are incommensurate. They are commensurate, pi. And at this point, when the charge starts to kick in, they become incommensurate, and the other value of the structure factor at the different wave vector kicks in. So that's the picture. The picture is that there are spin correlations that develop at a much larger scale, typically 0.4 times the hopping, something like this, and then they grow, and eventually the charge kicks in, but at the lower temperature scale. Okay, so just to conclude that part, this is a beautiful example, I think, of how one can move from the picture that was established from zero temperature wave function methods to finite temperature following the melting of this stripe in connection with how the spin correlation. Okay, so now more about the spin correlations in the pseudogap, and yes?
What was U over T when you were seeing these commensurate charges?
I think U over T in this paper here was 8, but I would have to check that because there is so many data that I think it's in this range. Okay, but I will check that at the break. Okay, so let me tell you a few things about the pseudogap. And the pseudogap, in my opinion, has been now clearly established by computational methods to be connected to spin correlations. So what is the pseudogap? Well, I'm going to take a very qualitative approach to that. It's a depletion of low energy spectra in specific regions of momentum space. If you would make a picture, like ZX is doing all the time, of the Fermi surface, we know that this is the famous truncation of the Fermi surface into Fermi arcs. And correspondingly, and this is how it was discovered, originally there is also a drop in the uniform susceptibility of point coding. So what do we know about the evolution of spin correlations? Well, if we go back to 30 years ago from just mean field theory, we can open this beautiful paper that I already quoted. No, that's actually a different one by the same author. And you will see a mean field phase diagram, just Hartley fog, okay, of temperature versus here density. So doping goes that way. And you see that there is a regime of, in Hartley fog, spin commensurate Lagrange order and a regime of incommensurate Lagrange order with an evolution from commensurate to incommensurate. Yes. And in fact, this suitably interpreted, because this is of course all crossovers because of Merlin Wagner, this picture is actually correct. We know that this happens, jumping now over 30 years of work. This is a very recent paper that does diagrammatic Monte Carlo, which study this evolution from commensurate spin correlations here centered at pi into incommensurate spin correlations here, which means if you want doing a cut like this, increasing doping. Okay. So again, these calculations show that spins take over the onset of spin correlations takes place at a much higher temperature than the onset of charge correlations. Here you see that down to T over T of about 0.1, there is nothing in the charge, but the spin has actually taken. Okay, so now let me tell you what we think is the connection between this growth of spin correlation and the pseudogap. And since I have 3 minutes to do that, this is going to be very, very brief. 3 minutes?
You have still 7 minutes.
Oh, 7 minutes.
Yeah.
That's fantastic.
Now we can answer.
Okay. So, oh yeah, because you gave me a warning at 10. That was
Yes,
the trick.
yes,
Okay, great. Thank you. So, let's start with an easy case. Let's do half filling. I know this workshop is about doped, but allow me to have a few slides on half filling. Half filling, weak coupling. Okay, or weakish coupling. You know, U over T equal to. Okay. So, in principle, we should be able to do everything on this problem, right? Well, in practice, this is a recent paper in which we've basically used every single finite temperature method under the sun to actually benchmark what can be said of the crossovers as a function of temperature in this problem. So we've called this a multi-messenger, multi-method paper because it uses like 15 different methods, and it also looks at many, many different correlation functions. Okay, I'm not going to review which ones. So again, this is what you would get if you do mean field. In this case, dynamical mean field. You would have a crossover between a very incoherent system at high temperature, a sort of metal at intermediate temperature, and eventually exponentially large spin correlations start to kick in. In reality, this is a crossover, and there is a subtlety here that the crossover from incoherent to metallic takes place in a different manner at the corner, at the nodes and the antinodes. There is a Van Hove singularity at the antinode, which actually lowers this coherent scale, and also the opening of the what will eventually become a gap in this half-field case at 0 temperature is also at slightly different temperatures, so that defines basically 5 different regions. And you can map out all these crossovers by measuring various things in these finite temperature methods. Importantly, there is a correlation length that grows basically exponentially, which is not completely obvious. It's obvious at low temperature when the gap has opened, because that's the nonlinear sigma model does. But at intermediate temperature where you have a metal, we also find sort of a different exponential growth. And despite the fact that the correlation length can be 10 lattice spacing in this case, which is very large because this is half field, you can still get a reasonably coherent metal, which was kind of a surprise to us. Okay, there is a pseudogap here, of course. Eventually there is a gap at 0 temperature. And the point I want to carry home, to drive home, is that the mechanism for the opening of the pseudogap has been understood for like 25 years in beautiful work, in particular by Wilke and Tremblay, who just noted that when you calculate the spin fluctuation diagram, the hotspots provide very large scattering rates. This is more or less the calculation. And the large correlation length is really what creates the pseudogap. And there is a criterion for that. The correlation length must be larger than the double wavelength Vf over T. So when this ratio is large, the very long range antiferromagnetic correlations open a pseudogap at the hotspots. And we see all these things in these calculations very, very clearly. We can even quantitatively map out the different regimes by comparing the correlation length, which is measured in the calculation, and the double wavelength. Okay, so this is the take-home for weak coupling. All methods agree that about these crossovers. Well, all reliable methods agree about these crossovers. The weak coupling mechanism of this pseudogap is well understood, goes back to Wilke and Tremblay, Chubukov, Schmalyan, and others, and it's induced by a diverging antiferromagnetic correlation length with a very precise, well, at least qualitative criterion for the opening of the pseudogap. So now what about strong coupling pseudogap? Well, this is an example where we move to larger coupling, U over T over order 6, and we actually looked at the doped system, and this calculation is done for finite T prime because it's meant to be relevant for cuprates. And in this paper, we've been able to actually obtain converged answers for the self-energy of the Hubbard model with 2 completely different methods. One is this diagrammatic Monte Carlo method summing the perturbation series, and the other one is doing cluster DMFT methods going to very large clusters, which for this range of parameters, intermediate U, which was chosen so that we're in the most favorable situation for our calculations, one has to say, and doping of about 4%, we were able to completely converge the calculations. I'll take your question in a second, and obtain something like this, which is the imaginary part of the self-energy along some path in the Brillouin zone, the usual path that crosses node and antinode, and revealing that near the antinode, one has a very large scattering rate, which is actually the thing that opens the pseudogap. Yes, Karen, you had a question.
Well, I think this answers it. So you're looking at the imaginary frequency self-energy and getting a gap from that. Is that
Well, not directly getting the gap. We are monitoring the drop in spectral weight at the antinode as a function of temperature, okay? Or we sort of refrain doing any dirty
zero
business with
frequency.
analytic continuation. We have criteria to read off everything, well, everything. At least what we would like to know from imaginary frequency. Okay, and in this case, two important things is that the pseudogap opens when the magnetic correlation length is not very large. So we do, in contrast to weak coupling, you do not need a large correlation length. You need substantial short-range magnetism, but you do not need a large correlation length to open the pseudogap. That's point one. And point two is that in contrast to the weak coupling mechanism, things are not opening dominantly at the hotspots, where the antiferromagnetic Brillouin zone crosses the Fermi surface, but actually at the antinode, at pi 0. And here you see very clearly that the antinodes, which is the black curve, this is the scattering, the opposite of the scattering rate, minus im sigma. And you see that this is largest at the antinode than at the hotspot. So the antinodes are hotter than the hotspot. Yes?
Very naive question, but I mean, if it's really local correlations that are important, then why does the K-space structure matter? I mean, why is the antinode or anything special?
No. Well, there is a Van Hove singularity near the antinode, which is actually playing some role in terms of phase-space scattering, you know. And the honest answer to your question is that a full, complete theory, analytical theory, of why short-range magnetic correlations induce a pseudogap has not totally settled. There are interesting ideas around. Subir and I and Matthias Scheurer wrote a bunch of papers comparing to SU2 gauge theories. There are additional ideas about fractionalized power magnons that are floating around. They revolve. Are you going to talk about this?
Yes.
Okay, great, wonderful. So that's a nice connection to this talk. All this relates to the question of how intermediate range magnetic correlations can actually create this phenomenon. I'm not saying we fully understand it, I'm just saying it happens. And it's not associated with fluctuating charge density waves. It's actually associated with spin correlation. That's what we see in the calculation.
When you say intermediate range, sorry, what does it mean? 10 sides, 2 sides?
5 sides, 4 sides is enough. I can show you concrete plots to document. Okay, actually we can apply to all these calculations what's called a fluctuation diagnostics, which is basically being a surgeon of the self-energy, you know, doing surgery on the self-energy and looking at it in various channels and so on. Loosely taking inspiration from the Parquet equations. And this was pioneered in this very beautiful paper. And what comes out of this analysis is that what actually creates the channel which is responsible for the pseudogap opening is indeed the spin channel near pi. Okay, so that's the conclusion of this fluctuation diagnosis of self-energy. So the take-home of the self-energy. So the take-home message is that there's been progress in establishing, we knew this from cluster DMFT for many years, but now establishing beyond any doubt that the 2D Hubbard model does develop a pseudogap at small hole doping, that at intermediate or strong coupling, you do not need a large correlation length for this to happen. You need sizable antiferromagnetic correlation, but not very long range, that the physics is spin physics, and again, progress analytical description is needed. Okay, so now in the -1 minute that remains, yes?
That's very exciting, but the question is, can you probe somehow that the spin plays the role, spin fluctuations plays such a dramatic role?
Yes, that's this. This is exactly how we do it. So we analyze which fluctuation channel contributes to the part, to the K points where the self-energy is large and opens the pseudogap.
But does it have some implication for spin susceptibility?
Yes, it has some implication for spin susceptibility. I showed you earlier a plot of the spin susceptibility. Where is this? Somewhere there was a plot of this, yeah, here. So here you see that the spin susceptibility takes off before the charge, right? And where it takes off, of course, this is a qualitative criterion because this is a crossover, is also where T star is. So,
Antoine?
yes.
So at weak coupling, you've made this argument that it's related to spin fluctuations. You also say it's stronger. In immediate coupling, it's related to this. On the other hand, it sounds like a pretty exotic description is needed. Do you think that these are continuously connected?
That's an excellent question. I see no evidence and no reason for which there should be a brick wall between these two regimes. It may very well be that this is a continuous evolution.
Is that consistent with these theories at the bottom?
I think so, yes.
So in
Yes.
finite temperature, they're smoothly connected, but
Yeah.
I see.
Now, here is the question. Thank you, Subir. What happens as we go down to low T or T equals 0? Okay, so that's the conclusion of my talk. We've actually addressed this question. We've interrogated these calculations with this question that has been prominent in the field for many years, which is we have this Pseudogap regime, we have this stripe ordering at T equals 0 and even at somewhat finite temperature, and we now agree on all these things, I think. So how does the Pseudogap evolve from, as we cool down, into a state of matter? Is there room for a state of matter in which the Fermi surface is reconstructed without any broken symmetry? Or is the fate of the Pseudogap to just hit the wall where stripe ordering sets in and becomes off? Okay, so that's the question. So we've made progress answering that question, again, for T prime equals 0, doing a little bit of a bold analysis of the diagrammatic Monte Carlo data, and this is what we do. What we do is we map out as a function of U and doping for several temperatures the region where the Pseudogap exists, which is the red region. And you see that as you cool down, this is the best that diagrammatic Monte Carlo can currently do in this range of temperature and doping. So this is, what, maybe 4 times cooler than what cold atoms can do, something like this. So, you know, it's a race, right? So you see this red Pseudogap region invading progressively the phase diagram, and the question is, can we extrapolate to T equals 0? So, you know, we have data only down to T equals 0.07, so this requires to be a little brave. But if we actually do that, to the best of the extrapolation that we can perform, we obtain that red line here as a function of U and doping. So now this is an extrapolated boundary from all these dashed lines of the Pseudogap region in the U versus doping range. And believe it or not, when we do that, we find that this boundary coincides with the boundary I showed you at the beginning of the talk, which separates stripes and no-stripes. So with a very heavy heart, and despite the papers Subir and I wrote together to, you know, get reconstructed Fermi surfaces without broken symmetry, which is a fantastically nice and interesting and exotic state of matter, our conclusion, and again, this comes with a grain of salt, there is an extrapolation here, is that in this case with T prime equals 0, the fate of the Pseudogap is to stripe order eventually. And, you know, even these theories, these analytical theories, also see discharge density and stripe ordering as a possible instability. Well, this is what it seems to happen. Okay, so miraculously, I'm not too late. I hope I convinced you that a lot of progress has taken place in the last decade or so. This is more or less what I already said, so I'm not going to elaborate more. If you want to know more, but perhaps not even the most recent things, because the field is moving very quickly, there are some recent reviews around Philippe co-authored, and I have also some lectures on the web at the Collège de France from a year ago.
Yeah, thank you very much, Antoine, for this fascinating talk. we have already had a lot of questions during the talk, but I would allow 1 or 2 more before we move to the next talk. Eugene.
Dan, can we go back to the phase diagram you just had?
Yes.
When you are saying no pseudo, so you have like prediction, yes, it's an instrumental prediction, pseudogap, no pseudogap, and probably the simplest measurement would be spin susceptibility, like we heard in the talks earlier. So you would say when there is no pseudogap, there will be no suppression of uniform spin susceptibility as we lower the temperature.
That's. I didn't show the results for the uniform spin susceptibility, but this is what I expect. Yes.
So and
Yes, I mean, T star. It's a classic way, even going back to the work of Alul and others, in cuprates to monitor T star as the place where the night shift drops.
so that's your falsifiable prediction. So scan U, scan doping, like either we see sort of spin gap opening up or we don't, we will know whether we believe your methods or we don't.
That's it.
Sounds simple enough.
Yep.
So, Fabian.
Yeah, so maybe a naive question. In the pseudogap regime, can we relate this somehow to magnetic or spin polarons that would fall?
Aha. Well, this is why I'm at this workshop. I would like to understand how the correlation functions we measure. Of course, we don't take snapshots, right?
Right, but even if we think of this classic Cayley read, right, where you have small pockets form, it seems that at pi 0 there should be a gap.
Well, yes, but there is a long way between the single hole problem and the full system. Otherwise, we wouldn't have been working for 3 decades, right?
That's also a state with correlation equals infinity, and he showed that when correlation is large,
Yeah.
it works. Everything, that picture is correct.
But I still think that there is a point here of trying to connect all these things that we are learning from simulating the large systems and measuring sort of standard correlation functions to what is seen locally in the microscopy experiments. And I think one should put work in bridging this gap. And perhaps some people have already done that, but I think that's...
Just following up on that, you guys can compute instantaneous correlation functions.
Yes.
But so far you showed us 2-point correlation functions, right? Like spin susceptibility, RPS.
You want multi-point.
We want multi-point correlation functions.
Yes, and I want cooler temperatures.
It sounds easier to get multi-point
We'll get
correlation.
there. Yeah, you're right, Eugene. Point taken.
Okay, so in the interest of time, let's thank Antoine again for this wonderful talk.